Hello, my name is Mike Raj, and today we'll be talking about thermodynamics, especially the first law of thermodynamics. This is for physical chemistry, GCU. First law of thermodynamics. What is thermodynamics? Thermodynamics is science that deals with energy production, storage, transfer, and conversion. Thermodynamics studies the effects of work, heat, and energy on a system. So there are like four laws to consider. Three effective laws. Um, the zeroth law is about the state of balance between all contending forces like heat, work, and stuff in question. So it's a equalization. Everything gets equalized. The first law. The first law is about energy and its utility. Second law is about temperature and its variability. The third law it is about entropy or disorder and its inevitability because everything breaks down. The first law of thermodynamics. The first law of thermodynamics states that energy can be converted from one form to another with the interaction of heat, work, and internal energy, but it cannot be created nor destroyed under any circumstances. And this is because of the law of conservation of energy. Refers to an isolated system in which there is no net change in energy, where energy is neither created nor destroyed. Although there is no change in energy, energy can change forms, for example, from potential to kinetic energy. In other words, potential energy and kinetic energy sum to a constant total energy for a specific isolated system. So once again, the first law of thermodynamics is about energy and its utility. Things to consider and remember. It is about energy and its transference and its interactions. It's all about energy. So what energy are we talking about? Um, the energy of the surroundings, the universal energy, and the internal energy. Here we're referring to not the surrounding energy or the universal energy, but the internal energy. Internal energy is also extensive, affected by outside forces. It's an energy that is changed by outside factors. Specific energy, which is an intensive property, is distinct of internal energy. Specific energy is the energy that is inherent in a system that can be affected by outside intervention. Work and heat can't be stored; needs to be used as it becomes available. Work and heat can't be stored because it's always in transference. It's always moving. Something is moving, then it's work. Temperature difference gradient changes, so that is heat. Isolated system energy remains constant. So when a system is isolated, its energy remains constant because it is encapsulated from outside forces. Conservation of energy can't be destroyed or created. The conservation of energy, which we previously mentioned, says that energy cannot be created or destroyed. Every system has internal energy but at rest and can be acted upon and will effect and affect work through transference of heat. So, so this is another definition of or I should say description of the first law. So it's a description of the first law. Good description. Every system has internal energy when at rest and can be acted upon and will effect and affect work through transference of heat. helps understand fluid dynamics. That's very important for engineering, for those who are engineering, like water, gas, plasma, anything that is moving. And as um, here we are not talking about chemical kinetics, which needs energy, but we are talking about thermodynamics. The difference between kinetics and thermodynamics is kinetics deals with small energy, small amount of energy, while thermodynamics deals with larger, with large forces. Indial energy is potential energy available for work. Stirling engine, that would be a prime example. The first law of thermodynamics, these are the another way that energy can change form is heat and work. As heat is applied to a closed system, the system does work by increasing its volume. So here is work, pressure exerted times the change in volume. This was another example of first law of thermodynamics, where the work exertion changes the pressure and volume and thus the internal energy. Another example would be a Stirling engine. This engine uses Stirling cycle, the utilization of temperature differences extremes for mechanical work, useful but little practical value due to its lack of commercial adaptability. It was created around 1816 by a pastor named Robert Stirling. It's amazing. The first law of thermodynamics, equations that need to be known. Delta E internal equals delta Q minus delta W. Q is heat and W is work done. So as we discussed, internal energy is the sum of the work exerted and the heat involved. The work and the heat combined. That is enthalpy, which is heat, another word for heat, equals U, which is internal energy. P is pressure and volume. So another equation. And this is the universe. So universal energy equals the system's energy and the surroundings energy. And the V is and the W is uh, pressure times volume. And PV equals nRT, where this is also involved in thermodynamics, and it deals with P is pressure, V is volume, N is moles, R is ideal gas constant, and T is temperature. Learning methods, active learning. So these are the active learning methods that can be employed for teaching chemistry. So they learn in small group settings using POGO or other actively guided group learning, where teacher educator is a facilitator. So that's one method. Small chunks of information explained and worked out, because sometimes I forget the meaning and hidden meaning of these variables, and so we have to understand what this variable means and then work on it. Videos showing examples made available for students. YouTube is very helpful to quickly review all the calculations, doing different kinds of problems, not only doing the easy ones, but doing also the hard and different ways of answering the same question. So students get a feel for it. Group presentation during group workshops. So it's another interesting active learning method, is that each during the group sessions, group workshops, each group will be assigned a subject for the day, and they will be required to explain the subject content around 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 15 minutes. And the single problem quiz at the beginning of class to encourage active learning and to teach retaining information. So another interesting active learning method would be to give them a pop quiz at the beginning or at the end, and help them to retain knowledge and help them to encourage learning and help them to go back and review. So it won't be from the last lessons covered. It would be like from it could be from the beginning of the class, beginning of the semester, and so forth. So it gives them it reinforces certain knowledge. So this is the first law. So this is the problem. A system does work on the surroundings with 500 joule. That's the work. Also, heat is transferred in the process of work, 500 joule. How much internal energy is used? So here the problem is asking what the work has this much energy, and the heat transferred in the process of work has this much energy. So how much internal energy is available? So delta U, which is mean the change in internal energy equals Q minus W, which is Q meaning heat minus work. So the Q here is 500 joules. Um, so it is minus because it's work done outside the system, in the surrounding. So it has to be negative. And this one, heat transfer will be positive because it's exothermic, not endothermic. Exothermic is positive, endothermic would be positive and exothermic negative. So it'll be also heat is transferred in the process of work. So this is because exposure of heat is negative and the work done is negative from the surrounding to the. I think there's a mistake here, but there will be no net internal change because each one is neutralizing it. So it will be negative, so it will be plus, and it will be around here zero because 500 joules of work are exerted and heat is transferred. So it would equalize and be 0 joules of internal energy. That is wrong. The second problem, this problem is taken from chemteam.info, website for high school chem students, used website. So here is PV equals nRT, where pressure, P is pressure, V is volume, N is moles, R is ideal gas constant, and T is temperature in Kelvin. So the question asks, a sample of gas at 25 degrees Celsius has a volume of 11 liters and exerts a pressure of 660 uh, mercury millimeter of mercury. How many moles of gas are in the sample? So here we just take PV equals nRT. We'll take this, this, and this. This is the temperature. That's the ideal gas constant. So here is conversion factor. We are turning into from mercurial unit to ATM. That's ideal. Note the conversion from mm to ATM and from Celsius to Kelvin. So this is Kelvin. It has to be in Kelvin scale. So the answer would be N is 0.391 mole. So that's the amount of mole available here. And another thing to note is the volume is in 11. It's in liters. The volume can be in centimeter cube or decimeter cube or some unit that describes volume. It doesn't have to be in liters. So the resources to use, POGO, it's a process-oriented guided inquiry learning. Pogo.org, it's a good website. This is my favorite website. chemlibertext.org, very helpful. YouTube helps uh, to know, um, easily find calculations and stuff. For search engine is also useful. DuckDuckGo is a useful search engine, and textbook ideally, because if you read the textbook, you will understand the concept, and once you understand the concept, then it will be easier. And the resources. So these are the four resources. And thank you once again for listening to the lecture on first law of thermodynamics. And I hope I did well. And thank you once again.